Welcome learners. This is second lecture on moments. In this video lecture, we are going to learn about the relationship between non-central moments and central moments. That is the expression of non-central moments in terms of central moments and properties of moments, Sheppard correction for moments to rectify grouping error and the uses or applications of moments. Also, the calculation of moments or the example for calculating first four raw moments and central moments. Okay, in the previous lecture, there are two subscripts. So I want to quickly recap the previous lecture, last slide. Here, this is the relationship between central moments and non-central moment. This is the expression of non-central moment in terms of central moments. We derived this in the previous video. If we substitute r is equal to 2, mu r, 2c 0, 2c 0, this will 2c 0, and in place of r 2, mu 2 dash, 2c 1, mu 2 minus 1, mu 1 dash, again this mu 1 dash, 2c2, mu 2 minus 2, 0, dash, this mu 1 dash whole square. Okay, up to 3 terms. 1, 1, 2, 3. 3 terms only comes. Okay, this is through 2, 3 terms occurs. Okay, this mu 2 is equal to, this is 1 into mu 2 dash, 2c2 2, mu 1 dash into mu 1 dash plus 2c2 1, mu 0 nothing but 1, mu 1 dash whole square. Here this is equal to mu 2 dash 2, mu 1 dash, mu 1 dash, mu 1 dash whole square plus this is 1 and this is 1, mu 0 dash is equal to 1, mu 1 dash whole square remains. Okay, here with minus sign 2 mu 1 dash whole squares with plus sign 1 mu 1 dash whole square. 2 minus 1 remains. Okay, this is mu 2 dash minus mu 1 dash whole square. Therefore, mu 2 is equal to mu 2 dash minus mu 1 dash whole square. Similarly, substituting r is equal to 3 in the equation, this is mu 3 is equal to 3c0, mu 3 dash, 3c1, mu 3 minus 1, mu 2 dash, mu 1 dash plus 3c2, mu 3 minus 2, mu 1 dash, and this is mu 1 dash whole square, 3c3, mu 3 minus 3, mu 0 dash, mu 1 dash whole cube. Now this is 1 into mu 3 dash minus 3c1 3 into mu 2 dash mu 1 dash plus 3c2 3 mu 1 dash into mu 1 dash square plus this is minus 3c3 is nothing but 1 and mu 0 dash remains, mu 1 dash whole cube here. Now mu 3 is equal to mu 1 dash minus 3 mu 2 dash mu 1 dash plus 3 into mu 1 dash whole square mu 1 dash whole power 3 minus this is 1, this is 1, mu 1 dash whole cube remains with minus sign. Here with plus sign 3 mu 1 dash whole cube with minus sign 1 mu 1 whole cube 3 minus 1 2 remains with plus sign. Here mu 1 dash whole cube minus 3 mu 2 dash mu 1 dash plus 3 minus 1 2 mu 1 dash whole cube. Similarly, if r is equal to 4, mu 4 is equal to 4c0 mu 4 dash minus 4c1 mu 4 minus 1 dash mu 1 dash plus 4c2 mu 4 minus 2 mu 2 dash mu 1 dash whole square. Okay, minus 4c3 mu 1 mu 4 minus 3 mu 1 dash whole cube in the formula, plus the last term is 4c4 mu 4 minus 4 mu 0 mu dash power 4. Okay, this is the second term. Here 4c0 1 mu 4 dash 4c1 4 mu 3 dash mu 1 dash plus 4c2 6 mu 2 dash and mu 1 dash whole square minus 4c3 4 mu 1 dash mu 3 dash whole cube plus 4c1 1 mu 0 dash mu 0 dash mu 1 dash whole power 4. This is nothing but mu 4 dash minus 4 mu 3 dash mu 1 dash plus 6 mu 2 dash mu 1 dash whole square minus 4 into mu 1 into mu 1 dash whole cube mu 1 dash whole power 4. Here 4 mu 1 dash power 4 and plus mu 1 dash power 4. Here these are with negative sign 4 mu 1 dash whole power 4 and 1 mu 1 dash whole power 4 minus 4 plus 1 minus 3 here. Okay, this is the first 4 central moments in terms of non-central moments. The earth non-central moment about any arbitrary point A is given by mu r dash is equal to, this is the definition for first non-central moment, earth non-central moment, fi xi minus a power r by n. Let u is equal to xi minus a. In the previous lecture I used d, ui is equal to xi minus a. We are subtracting a from every value. Now this mu r dash is equal to I is equal to 1 to n fi instead of xi minus a ui power r. If a is equal to xi minus a by h, here h is the class interval or width of the class, then mu r dash is equal to I is equal to 1 to n fi ui power r by n into h power r. This is the formula. If we take deviation to calculate non-central moments, we use this formula. Similarly, the first raw moment, first non-central moment is equal to sigma fi ui by n into h, and second raw moment is fi ui square by n into h square. Third non-central moment is equal to I is equal to 1 to n fi ui power 3 by n into h power 3. Fourth non-central moment is equal to fi ui power 4 by n into h power 4. Generally, we use this formula to calculate non-central moments. This is the deviation. And the definition of non-central moment, the earth non-central moment is mu r is equal to 1 by n into I is equal to 1 to n fi xi minus x bar power r. Instead of a, in non-central moment, these are moments about mean. Here let z is equal to zi is equal to xi minus x bar. Then mu r is equal to, in place of xi minus x bar, keep zi power r. If r is equal to 0, r is equal to 0, 1 by n into I is equal to 1 to n fi xi power 0. Anything power 0 gives 1. Sigma fi is nothing but n by n 1. Mu 0 is equal to 1 always. Similarly, if r is equal to 1, here 1 comes. Anything power, no, here the sum of deviations taken from their arithmetic mean is 0. So this term become 0. The whole term become 0. So the first non-central moment is 0, and if r is equal to 2, mu 2 is equal to I is equal to 1 to n fi xi minus x bar whole square. This is the second order average. This is the second order average taken from mean. So this is second central moment is nothing but variance sigma square, whereas root of sigma square is standard deviation, that is sigma. And if r is equal to 3, mu 3 is equal to 1 by n into I is equal to 1 to n fi xi minus x bar power 3. If r is equal to 4, xi minus x bar power 4. If we want to calculate non-central moments by using this formula, it is somewhat difficult. This term involves power 4. This is power 3. So generally we use non-central moments to calculate central moments by using the relationship between central moments in terms of non-central moments. First we calculate non-central moments, first four non-central moments, mu1 dash, mu2 dash, mu3 dash and mu4 dash. By using the non-central moments only we calculate central moments. So up to when you need the statistics career, you must remember the first four non-central moments in terms of first four central moments in terms of non-central moments. These are the formula. Mu2 is equal to 2 terms, mu3 is equal to 3 terms, mu4 is equal to 4 terms here. If mu2 occurs, mu2 dash, first term, mu3, mu3 dash, mu4, mu4 dash. Look at the last term. For all the moments, last term is mu1 dash only. If 2 here, 2 here, 3 here, 3 here, 4 here, 4 here. The coefficient of the last term is 2 minus 1, 1 here. 3 minus 1, 2 here. 4 minus 1, 3 here. This way you can remember the central moments in terms of non-central moments. By the definition of non-central moments, now we already discussed the relationship between central moments in terms of non-central moment. In the lecture, in this video, we derive the relationship between non-central moments in terms of central moments. By the definition of non-central moments, we know that mu r dash is equal to 1 by n into I is equal to 1 to n fi xi minus a power r. I just subtracted and added x bar to this here. Xi minus x bar plus x bar. Okay, minus a. Now, this becomes 1 by n into I is equal to 1 to n fi xi minus a is equal to z. We have already seen this is the transformation. Xi minus x bar is equal to zi. Look here. We know the mean is nothing but a plus first raw moment, first non-central moment. A plus sigma fi ui by n into c. Okay. From this, mu1 dash is equal to x bar minus a. This a subtracts x bar. So instead of x bar minus a, we can use mu1 dash. So instead of x bar minus a, mu1 dash I have used it. This is the repetition. Instead of x minus y, here x plus y, rc0, x power r, y power 0, rc1, x power r minus 1, y power 1. This is binomial expansion for r terms. Just expand this zi minus mu dash, mu1 dash power r by using binomial expansion. This 1 by n, I is equal to 1 to n, fi remains here. I am expanding this. This is first term, this is second term. Instead of x, zi here. Instead of y, mu1 dash here. Just expand rc0, zi power r, y, mu1 dash power 0. rc1, zi power r minus 1, mu1 dash power 1. rc2, zi power r minus 2, mu1 dash power 2. Plus so on, rcr, zi power r minus r 0, mu1 dash power r. This is the expansion. Take this 1 by n summation fi inside the bracket, multiply all these terms, rc0, this is 1 by n fi, 1 by n fi sigma summation I is equal to 1 to n fi into zi power r mu1 dash power 0. So this term becomes 1. This is rc1, 1 by n I is equal to 1 to n fi zi power r minus 1, same. Look here, the last term fi summation I is equal to 1 to n fi by n is 1 and this RC1 is equal to 1, Zi power 0 is equal to 1. So the last term is mu1 dash whole power R. Now this is the expression of mu r dash in terms of central moments. Here in this expression non-central moments also occur, whereas in central moments only non-central moments occur. Here both central and non-central moments occur. Mu r plus rc1 mu r minus 1 mu1 dash. This instead of this we can use mu r minus 1. This is nothing but the rth central moment. Rth central moment. I is equal to 1 to n fi Zi power r is nothing but rth central moment, where Zi is equal to xi minus x bar. So this is mu r, first central moment. This is the first rth central moment. This is r minus 1th central moment. This is r minus 2th central moment. The next term is r minus 3 central moment. Mu r minus 3 is equal to I is equal to 1 to n fi Zi power r minus 3. So this is the expression of non-central moments in terms of central and non-central moments. By using this expression, we derive first four non-central moments in terms of central moments. Simply, if r is equal to 2, this is 2, minus not minus, this is equal to 2, mu2 dash is equal to mu2 dash is equal to mu2 plus 2c1 mu2 minus 1 mu1 dash plus 2c2 mu2 minus 2. This is mu 0. Mu 0 is equal to 1. Mu 0 is equal to 1. So this is 1, this is 1, mu1 dash whole power whole square remains here. So this is mu2 dash is equal to mu2 plus 2c2 2 mu1 dash mu1 first central moment, and this is mu1 dash plus this is only mu1 dash whole square remains here. You all remember first central moment is 0. So this term vanishes. Mu2 dash is equal to mu2 plus mu1 dash whole square only. This term vanishes. And if r is equal to 3, mu3 dash is equal to mu3 plus 3c2 3c1. This is 3c1. This is 3c0 1. 3c1 mu3 minus 1 mu1 dash. 3c2 mu3 minus 2 mu1 mu1. So this term also vanishes. Term also vanishes. This is 3c3 mu3 minus 3 become 1 mu0 1. So this is mu1 dash remains here. So this is mu3 dash mu3 plus this term total term vanishes. 3c2 is equal to 3 mu 3 minus, okay, this term vanishes. 3 minus 2 mu 1, this term vanishes. This mu 3 minus 1 mu 2 mu1 dash, this term vanishes. 3c3 1 mu1 dash whole cube. Similarly, if r is equal to 4, mu4 dash is equal to mu4 4c1 mu4 minus 1 mu1 dash mu4c2 mu4 minus 2 mu1 dash whole square 4c3 mu4 minus 3 mu1 dash whole cube 4c4 mu1 dash whole power 4. This is 1. Here also, here this term vanishes. This term vanishes. Mu4 4c1 4 mu4 minus 1 mu3 mu1 dash 4c2 6 mu4 minus 2 mu2 mu1 dash square remains. This term vanishes. 4c1 4c4 1 mu1 dash whole power 4. So these are the expressions of non-central moments in terms of central moment. Let us look at the effect of change of origin and scale on moments. If we add or subtract an arbitrary value to the variable, then that arbitrary value is called origin. If we divide or multiply with an arbitrary value to the variable, then arbitrary value is called scale. So here let u is equal to x minus a by h. A is the arbitrary value, h is the interval or width of the class. X minus a is equal to this u into h into u. This implies x is equal to a comes RHS, a minus a becomes plus a plus hu. Instead of x, you can use a plus hu in this by using this transformation. Similarly, x bar is equal to a plus h into u bar. Simply, in place of x, we can use x bar. This is u is the variable here. A and h are the constants. X subtract x minus x bar. X minus x bar is equal to a plus hu is x minus a minus hu. Plus a minus a gets cancelled. H common, u minus u bar remains. So instead of x minus x bar, we can use h into u minus u bar. Now, the rth non-central moment of a variable x about a is mu r dash is equal to, this is the definition of non-central moment. Instead of x minus a, where is x minus a? We can use hu. This h power r comes here. H power r comes here. 1 by n, I is equal to 1 to n, fi ui power r. This is up to this nothing but the non-central moment of variable u. So h power r into mu r dash. This is h power r times non-central moment of u. Whereas this is non-central moment of x bar, x, variable x. This is variable x. And if we transform u into x minus a by h, we are subtracting a from the variable and dividing with h. The a does not affect on the moment and h is affect. If we divide, we need to multiply. That is the difference. And now rth central moment of variable x about x bar is mu r is equal to 1 by n, I is equal to 1 to n, fi xi minus x bar power r. This is the definition of rth central moment. Instead of x minus x bar, we can use h into u minus u bar. H into u minus u bar. Here, this h comes here. H power r comes outside. 1 by n into summation I is equal to 1 to n, fi ui minus u bar. Similar, this is similar, but this is non-central moment of variable x and this is non-central moment of variable u bar, variable u. So this is h power r times non-central moment of u, h power r times central moment of u. So the moments are independent of change of origin. If we add or subtract any arbitrary value to the variable, does not influence the moment. But if we multiply or divide the variable, this we need to, if we divide, we need to multiply the moment. This is the relationship. These are the properties of moments. There is a question, show that moments are invariant to the change of origin and dependent to change of scale. So you have to write this proof. The Sheppard's correction for moment. In case of grouped frequency distribution, generally while calculating the moments, we assume that the frequencies are concentrated at the middle point of the class interval. That is, if 0 to 10, 10 to 20, We take the midpoint 5, 15 like that. 0 plus 10 by 2 gives us 5. 10 plus 20 divided by 2 gives us 15. So we are assuming that the total class is concentrated in the midpoint. This assumption is generally true for symmetrical distributions. We are already discussed what is symmetrical distribution. The symmetrical distribution, in case of symmetrical distribution, this assumption holds good. Also, it is true for moderately skewed distribution in which the class intervals are not greater than 1/20th of the range of the distribution. This assumption leads to symmetric error or grouping error in the even moments. Only even moments affected. To rectify this error, Professor Sheppard suggested some corrections to moments called Sheppard corrections to moments. He suggested correction. The mu2 corrected is mu2 uncorrected. Mu2 uncorrected means the calculated mu2 minus h square by 12. Here h is the class interval or width of the class. Similarly, mu2 corrected is mu3 corrected. There is no correction for the mu3. Mu3 uncorrected. And for mu4 uncorrected minus 1 by 2 of mu2 uncorrected plus 7 by 240 of h power 4. Here h is the class width. You must remember these corrections for Sheppard. Let us discuss the applications of moments. Moments are useful to find different statistical averages. They are the first moment of origin is nothing but mean, that is first raw moment, first central moment. And second moment about mean is called variance. And the measure of skewness is calculated by using the third central moment, that is the coefficient of skewness gamma 1 is equal to root of beta 1, where beta 1 is equal to mu3 square by mu2 cube. And the measure of kurtosis is calculated by using fourth central moment. We have, for measuring kurtosis, only moments measure exist. For skewness, there are Carl Pearson measure and Bowles measure, whereas to calculate kurtosis, there is only moments measure. The coefficient of kurtosis gamma 2 is given by beta 2 minus 3, where beta 2 is equal to mu 4 by mu 2 square. We first calculate the first 4 raw moments and first 4 central moments. The first raw moment gives us mean. Second central moment gives us variance. Third central moment is used to calculate coefficient of skewness. Fourth central moment and second central moment is used to calculate the coefficient of kurtosis. So the moments are very much useful to describe, to calculate the measures of dispersion, all the measures of descriptive statistics. Okay, to describe the statistics we need central tendency, dispersion, skewness and kurtosis. To measure all these 4 characteristics we use the moments. Let us discuss one example for easy understanding of the concept moments. Compute first 4 moments about the point 45 and first 4 central moments to the following data. This is the data. Class interval is 10 to 20, 20 to 30, up to 70 to 80. These are the frequencies. To compute first 4 non-central moments, and first 4 central moments, the first 4 non-central moments are, this is the first non-central moment. Here u is equal to x minus a by h. This is mu2 dash, mu3 dash, mu4 dash, where u is equal to x minus a by h. The central moments are, these are the first 4 central moments. First, for the given data, we need to find the mid value and u deviation, fi ui, fi ui square, fi ui cube, fi ui power 4, and the summations. This is sigma fi, and these are the sigma fi ui square, fi ui cube, fi ui power 4. By using these summations, we can find first 4 non-central moments. A is equal to 45. This is 45. And H is 10, class interval. This is H into 1 by sigma FIUA. H is 10. Sigma FIUA is 16. N is 300. Okay. Similar to, these are the first 4 non-central moments. By using these non-central moments, we calculate first 4 central moments. Mu2 equal to mu2 dash minus mu1 dash whole square, 113.72. Mu4, mu3 is equal, this is mu3. Mu3 dash minus 3 mu2 dash mu1 dash plus 2 mu1 dash whole cube. This is mu3 minus 4 into minus 3 into mu2 dash. This is mu2 dash 114, like that. Look here, mu4 is the 5-digit number. Similarly, compute beta 1, beta 2 coefficients and Sheppard correction for the grouped data. This is the data. These are the first 4. These are the first 4 non-central, first 4 central moments. These are first 4 central moments. Here they use direct method. By using direct method without calculating raw moments. This is Sheppard correction. Here, look here. This is 6-digit number fi into xi minus x bar. First calculate x bar sigma fi xi, mid value sigma fi xi. Subtract x bar from every x. This is, and this is fi into this, fi into square of xi minus x bar, fi into cube of xi minus x bar, summations. Directly we can find mean is equal to this. This is first central moment. First central moment is 0. Okay. 0.00047. These are second central moment, third central moment, fourth central moment. By using third and second central moments, we can find beta 1 coefficient of skewness. This is positively skewed, and these are corrections. Okay. Okay, from the video lecture, we have discussed relationship between non-central moments and central moments, properties of moments, that is the effect of change of origin and scale on moments, central and non-central moments, Sheppard correction for moments for mu3 and mu4, and applications of moments in calculation of different statistical averages with an example. Thank you.